Hello everybody and welcome back to Regents Chemistry. Today we are going to start a new unit which is about the acids, bases, and salts. So let's begin our discussion today with the different theories about acids and bases and salts. Now if you guys go to your reference table packet and then go to table K and table L, that is where you're given some common acids and bases. Now, of course, there are a lot more acids and bases out there, but these are the ones that you guys need to know at this point. So if we quickly talk about how these acids and bases are named, let's start with the acids. The first acid that we see in this table is HCl, which is hydrochloric acid. Now, hydrochloric acid is a little bit different than other acids because we also see the hydro part, but then we have the Cl, so we just named that as, so Cl is chlorine, and then we change the last part by making it an ic acid. So that chlorine becomes a chloric acid. And next up we have HNO3. So once again, now HNO3, the way it's different from HCl is that we are not talking about the hydrogen, and we only look at the NO3 part, which is nitrate. So we take off that last part, the ATE, and we substitute that with an IC, so it becomes nitric acid. Same thing with H2SO4. SO4 is sulfate, so that becomes sulfuric acid. PO4 is phosphate, that becomes a phosphoric acid. CO3 is carbonate, that becomes a carbonic acid. And then the C2H3O2 is acetate, that becomes acetic acid. So that is basically how we name acids for the most part. Bases are a little more simple compared to acids because if you look at the first base that is given there, we have NaOH. So Na is sodium, and then OH is just hydroxide. So we basically just name the ions that we see there. Next up, we have K, which is potassium, and then OH again is hydroxide. Then we have Ca, which is calcium, OH is hydroxide. And then NH3 is basically just ammonia. Now let's jump right into the different theories for acids and bases. The first theory that we are looking at is by Arrhenius. It's called Arrhenius theory of acids and bases. So this guy said that acids always have a hydrogen. And when they are in an aqueous solution, they release that hydrogen, which means they get rid of that hydrogen, the H positive ion. And that is basically what tells us that this is an acid. And here are some examples. We have HCl, HBr, H2SO4. All of them have that hydrogen in them. And when they are in an aqueous solution, according to Arrhenius theory, they are going to let go of that hydrogen. And then that positive hydrogen ion is going to be the only positive ion in the solution. And normally, because it's a solution with water, that H positive can combine with the water and it makes this H3O positive, which is also known as hydronium ion. So normally H positive ions do not exist alone just by themselves. They just make a bond or they attach with the water molecule and make hydronium ions. Now, some of the characteristics that can help us identify an acid other than if we are looking at the equation and we see that hydrogen going off, that's when we can tell that, well, this one is the acid. But if you're observing that in, let's say, a lab, we have a solution and we want to know whether this is acidic or basic, then some of the things that we know about acids are that they can conduct electricity, so they are good electrolytes. And then another way to identify an acid is if we test that using a blue litmus paper, it will turn red. So this is basically what that looks like. We have that blue litmus paper and then we pour a drop of acid on there and that part will turn red. Another type of indicator that we use to identify acids is phenolphthalein, and when we pour a drop or two of that thing in an acid, it will just go colorless. So nothing will happen, and that should tell us that this is an acid. And then finally, the pH of acids is less than 7. We'll talk more about pH in the next topic and also how do we test the pH of anything. So hang tight on that. But for now, just remember that pH of acids is less than 7. because this is the information that you'll need to know for the next part. Some more things to know about acids are that they contain a high concentration of the hydrogen ions, and because normally they are in an aqueous solution, and we said that the hydrogen ion combined with water to make a hydronium ion, so we see a huge concentration of those hydronium ions in an aqueous solution of acids. They also taste sour. You should never be tasting acids though. And as we said, they do conduct electricity. And basically, when we have a solution of an acid, the more acid we have in it, which means the greater concentration of acid that we have in our solution, the better it is going to conduct electricity. And so if you're looking at an acidic solution that is a very good conductor, it's going to be a strong acid. And if you're looking at an acid which is a poor conductor, which means it doesn't really conduct electricity that well, that's going to be a weak acid. And then finally, a super important thing to know about acids is that they are corrosive. Corrosive is something that can react very badly with human cells, which is why we should never be interacting with acids barehanded. We should never try to eat or drink it. Never do all that stuff. Just be safe. And because of this property, acids can be used to clean different different metals. Acids can also react with certain metals to produce hydrogen gas. For example, if you look at your reference table J, which is about the activity series, all of the metals that we see above the hydrogen, so above that H2, all of them they do have the tendency to react with any acid that contains hydrogen and produce hydrogen gas. Now, for the bases, Arrhenius said that bases have a hydroxide ion. So just like it said that acids have a hydrogen ion, it's saying that bases have a hydroxide ion, which has that -1 charge, and it releases that hydroxide ion whenever it is in an aqueous solution. For example, here are some compounds that can be bases according to Arrhenius theory. So sodium hydroxide, potassium hydroxide, calcium hydroxide, all of them have that hydroxide part, which can, when they dissolve in an aqueous solution, that hydroxide ion can be released into the solution. And then it's going to be the only negative ion in that aqueous solution. Now, some of the characteristics of bases, which are given in table L in your reference table packet, is that they're also good conductors of electricity, so they're electrolytes. If we want to test them using a litmus paper, we can take a red litmus paper, and if we pour a drop of our basic solution on that paper, it's going to turn blue. And if you're using a blue litmus paper, it's just going to remain blue. And if you're using phenolphthalein to test a basic solution, we have the solution, we put a few drops of phenolphthalein in it, the solution is going to turn pink. And finally, the pH of any basic solution is always going to be greater than 7. Remember, acids had a pH less than 7, bases have a pH greater than 7. Some more characteristics of bases include a high concentration of hydroxide ions, just like acids had a high concentration of hydrogen or hydronium ions. Bases taste bitter, and they are kind of like, they have this slippery, soapy kind of texture. And as we said, they can also conduct electricity, same thing, just like acids. The greater the concentration of a base that we have in a solution, the better it's going to conduct electricity. So if we have a solution that is 6 molar, and we compare that with a 1 molar solution of a base, the 6 molar is going to be a better conductor. And again, if a solution is a very good conductor of electricity, it's a strong base. If it's a poor conductor, that's a weak base. And finally, bases are caustic, which means they can dissolve your skin. So once again, we have to be very careful when using the bases as well. So now that we know what Arrhenius said about acids and bases, let's quickly practice what we have learned so far. So here we have 4 different compounds, and we have to identify an Arrhenius acid. Remember, Arrhenius said that acids need to have a hydrogen so that they can release the hydrogen ion into the aqueous solution. So if you look at the 4 options, the only option that does have a hydrogen, which can potentially release the hydrogen ion into the solution is option 2. Option 1 does not have either hydrogen or a hydroxide. Option 3 has a hydroxide, which means it's an Arrhenius base, and option 4 also has a hydroxide, which means that is an Arrhenius base as well. And that leads us to talking about the salts. So now we know that acids, according to Arrhenius theory, need to have a hydrogen ion, and bases need to have a hydroxide ion. So salts, when they're in the middle, they have a positive ion, any positive ion out there in the world other than the hydrogen, and they have a negative ion other than a hydroxide. So they can only not have a hydrogen or a hydroxide, but if they have any other positive or negative ion, that is most likely a salt. So for example, over here we have sodium chloride. So sodium is the positive ion, chlorine is a negative ion. Sodium is not a hydrogen and chlorine is not a hydroxide. So that's a salt. And one thing to know about salts is that they can also conduct electricity. So now we know that acids, bases, and salts, all three of them are electrolytes. They can all conduct electricity. Now, one thing to keep in mind here while we are talking about the acids and bases is that eventually we will talk about organic compounds when we get to organic chemistry. And there are different types of organic compounds out there, and two of them are organic acids and alcohols. Now, some of you might get confused when we are talking about those two. You might get them confused with the acids and bases. Now, here's the deal. Organic compounds have a functional group with them. So functional group is basically just a part of a compound that is always going to be with those type of organic compounds. For example, organic acids always have a functional group COOH with them. And then there's another like carbon related compound part like before with that COOH that is attached to that functional group. Now, if you guys look at that functional group, it has a hydroxide at the end, an OH. You might think it's a hydroxide, but it's not. It is the functional group, the whole thing, the COOH, and that is an organic acid. It's not a base. So that is one thing to be familiar with and to take care of. And then same thing with the alcohols. They also have that hydroxyl group at the end, but they're not bases. That is just a functional group that is always with any type of alcohol. All right, moving on. So there are these new type of reactions called neutralization reactions associated with Arrhenius acids and bases, which basically include an Arrhenius acid reacting with an Arrhenius base, forming salt and water. For example, over here, we see an acid, which is HCl, a base, which is NaOH, reacting to form water, and salt, which is NaCl. Now, if you guys notice, the sodium and the chlorine part in this reaction are going to combine together and they are going to make that salt, the NaCl. And then the hydrogen and the hydroxide part of the acid and the base are going to combine to make water. And that's how a neutralization reaction goes. So let's look at these problems to practice that really quickly. In the first problem, we have sodium hydroxide reacting with nitric acid. Now, the sodium and the nitrate, the Na and NO3 are going to react together to form sodium nitrate, which is then going to be the salt, and then the hydrogen and the OH, hydrogen and hydroxide, are going to react to form water. Same thing with the next question. The calcium and the SO4 are going to react to form calcium sulfate, which is going to be the salt, and then the hydrogen and the hydroxide are reacting to form water. Just make sure you guys have already learned the balancing equation, so make sure that your equation is balanced. So in this case, because overall we have 2 oxygens and 4 hydrogens, so that's going to be 2 water molecules, not just one. So that's one thing to take care of. All right, now let's talk about an alternate theory for the acids and bases, which is called the Bronsted-Lowry Theory. Now, these two people basically defined acids and bases in terms of the transfer of a proton, which is an H positive ion. So H positive ion is also known as a proton. You guys know that from the Atomic Concepts chapter. So this theory says that acids are proton donors, which means because they have an H positive ion in them, they are going to donate that to something else. They're going to get rid of that H positive, which is basically the same thing that Arrhenius said, that acids are going to release their H positive ion. That's exactly what acids are doing in this case as well. Bases, on the other hand, according to this theory, are going to be the proton acceptors. So instead of talking about the hydroxide now, we are saying that bases are simply just accepting the proton that the acid is giving off, or that the acid is donating or releasing. So bases accept, acids donate. That's basically what Bronsted-Lowry theory says. So if you look at this example, we know that HCl is our acid. Why? Because HCl is getting rid of its hydrogen on the other side. It's releasing its hydrogen. That's how we know that because HCl is donating the proton, it's an acid. Water, on the other hand, is then accepting that proton from HCl, and it's becoming a hydronium ion. So we know water is then going to be a base according to Bronsted-Lowry theory. Here's another example, the HNO3, the nitric acid. We notice that it does have a hydrogen on the reactant side, but on the product side, it donated that hydrogen. It released it, got rid of the hydrogen. So that's how we know that HNO3 is going to be the acid, because it's donating the proton. The H2O is, however, accepting an additional hydrogen, because on the product side, it's now becoming a hydronium ion, H3O. So that's how we know that H2O is acting as a base in this case. So now what happens is that, according to Bronsted-Lowry theory of acids and bases, after the acids have donated their hydrogens and the bases have accepted a hydrogen, a proton, they make that relationship with each other that we call the conjugate acid-base pair. So basically, a conjugate base is whatever is left off after the acid has donated its proton. For example, in this example that we see, the acid is CH3COOH, which is the acetic acid, and after it has released its hydrogen, forming that acetate ion, that is going to be the conjugate base, because that is what's left off after the acid has donated its proton. And then a conjugate acid is then going to be whatever is formed after the base has accepted a proton. So for example, the base in this case is H2O. So on the product side, the H3O positive is the one that is going to be the conjugate acid, because it has now accepted a proton. So let's quickly practice that as well. Now here we have a reaction. On the reactant side, we see NH4 positive, which has 4 hydrogen ions right now. We notice that on the product side, this NH4 positive just released or donated one of its hydrogens, so now it's only NH3, which means the NH4 positive is our acid, and then on the product side, after it has donated its protons, that is our conjugate base. For the bases, the OH is, we notice that the OH has accepted a proton on the product side, so that means our OH is the base, and then the H2O, which is what we have after the base has accepted a proton, is now going to be our conjugate acid. Here's another example. We have the phosphoric acid H3PO4. We notice that it is going to donate one of its hydrogens because it has 3 hydrogens right now, but on the product side, we only notice two hydrogens in this compound. So that tells us that H3PO4 is our acid, and then the H2PO4, which is what we got after this acid donated its hydrogen, that would be the conjugate base. On the flip side, the NO2, we notice that this gained a hydrogen in the product side. So that means the NO2 is our base, and then on the product side, where it has accepted a hydrogen, a proton, that's going to be our conjugate acid. And then finally, the very last concept to go with the Bronsted-Lowry theory of acids and bases is the amphoteric substances. So these are the substances that can sometimes act like an acid, but they can also sometimes act like a base. A very common example of that is water. So for example, here we see this reaction where we have two water molecules reacting with each other to form hydronium and hydroxide. Now, one of the water molecule here is an acid and the other one is a base. So water number one is an acid. Why? Because it is donating one of its hydrogens. So that on the product side, we only have a hydroxide left. Water number two is going to be the base because it is accepting that previously donated proton from the other water molecule. So now it is a proton acceptor and it becomes a hydronium ion. So that's how some substances out there can act as both an acid and a base. Alrighty, that's it for now. Take care. I'll see you guys in the next one.